Okay, example number 3, we are still on section 3.2, part 1. So example number 3, evaluate the indefinite integral. We've got sine to the 8th of r, cosine cubed r dr. And so what I'm going to do is just kind of start peeling things away and seeing what we can do to make this work. We know that if we make u equal sine x, then our du would equal, I guess we're r, sorry, sine of r. Then our du would equal cosine r dr. So that looks doable to me. So let's rewrite. We've got sine to the 8th r. Then if we peel one off, we would have cosine squared r, which is okay because we know we can rewrite cosine squared r to be in terms of sine squared. And then we peeled off one cosine r dr. So let's say this cosine r dr is going to be our du. Then for this, we would have u equals sine r. And then we would need to rewrite this as 1 minus sine squared r. Okay, so then now we can go ahead and, I guess I should rewrite that one more time. We can start making shortcuts later. So this would be sine to the 8th r, 1 minus sine squared r, and cosine r dr. Now let's do all of our substitutions. So we get the integral of u to the 8th times 1 minus u squared du. And we're ready to integrate. And so, oh, actually, I'm going to do one more step. Let's go ahead and multiply that through. So we have u to the 8th minus u to the 10th du. And now the integral is 1/9 u to the 9th minus 1/11 u to the 11th. And now we're ready to substitute back in. So our final answer is 1/9 sine r to the 9th minus 1/11 sine to the 11th r plus c. And that's your final answer. Okay, on example number 4, they've kind of switched things up on us. So now the bigger exponent is second, which is with the cosine, and the smaller exponent is here with the sine. So I'm going to switch these around, and let's rewrite these, because I want to write it so that my biggest exponent is first. Okay, and now I've got an odd exponent here. So let's see what happens if I peel off a sine cubed x, or no, just a sine from the sine cubed x. I'll have cosine to the 8th v and sine squared v times sine v, oops, sine v dv. Okay, so this right here is what I want my du to be. So if I want sine v to be my du, then that must mean that, oh, that's supposed to be a cosine to the 8th. Cosine to the 8th v sine squared v. Yeah. I want this to be du, so therefore a cosine would have to be a u. And then the sine squared v, we could rewrite that to be 1 minus cosine squared v. Okay, so I'm going to rewrite one more time to include my substitutions. And then up here, we know we want to say u is equal to cosine of v. Now we've got to be careful here because there is going to be an extra negative we're going to have to make sure we keep track of. So because the derivative of cosine is equal to negative sine v dv. Okay, so we've got the integral of the cosine 8v of 1 minus cosine squared v and then sine of v dv. And now we can do our u substitution. So we've got the integral of u to the 8th 1 minus u squared, and then du. Okay, so multiply that through, we get the integral of u to the 8th minus u to the 10th du, which is then 1/9 u to the 9th minus 1/11 u to, oh, we forgot our negative. Ooh, I knew I was going to do that, didn't I? Alright, when we do this substitution back in with our du, we're going to need to make sure and put in a negative. So that's going to make all of the signs change on these. So keep that negative out in front. That's going to make a negative there and a positive here. So then I'm going to rewrite that so my negative's not out in front. So 1/11 u to the 11th minus 1/9 u to the 9th. That was a close one. And then plus c. Now we can substitute back in for u. And so I get 1/11 cosine to the 11th v minus 1/9 cosine to the 9th v plus c. And that is our final answer. Okay, example number 5, we've got the integral of cosine x, the square root of cosine x, sine x dx. So again, this end part right here looks like that would make a great du. So let's do a cosine for u. So u equals cosine x. Let's see if that's going to work. So if we had u equals cosine x, again, hopefully I won't forget my negative. So du is going to equal negative sine of x dx. Okay, so let's rewrite. Doing our u substitution, we've got the integral of the square root of u, and then just du with a negative. And yeah, then we're ready to integrate. So this would be u to the 1/2. So we're going to add 1, get 3/2, divide by that number. So we get negative 2/3 out in front, u to the 3/2 plus c. And then our final answer will be 2/3 cosine x to the 3/2 power plus c. And we got a negative. Yep, looks like we got it all in there. Okay, we are also going to be going over the products and powers of tangent and secant. So just a few things here to remember. So we've got the derivative of tangent x is equal to secant squared x, and the derivative of secant x equals secant x tangent x. We're going to have to keep that in mind. These ones are a little bit different as we're looking at these next examples. Also remembering what our integrals are for secant squared x, integral of secant x tangent x. Okay, you can keep track of any of those as we go along if we need them. And our Pythagorean identities. So we talked about them before. We've got tangent squared theta equals plus 1 equals secant squared theta. We can rewrite either one of those. So that's in terms of secant squared theta. We can also subtract the 1 from both sides and solve for tangent squared theta if we need to. Okay, so let's go on to example 6. Okay, so for these ones, we're going to have to look at them a little bit differently. We have our tangent to the 6th x and secant to the 4th x. So I am going to peel off 2 of these secants, and you can just kind of play around with them. There might be more ways to do them than just one. But for this one in particular, let's try tangent to the 6th x. Let's try splitting up our secant squared. So whereas before we wanted those, we were really looking for those even or odd numbered exponents, this time we're interested in the even numbered ones also, because I need a secant squared x to substitute a u for tangent. So if we have a secant squared x, that one's left over, and peel off another secant squared x dx, then right here can be one of my derivatives, or a du. Okay, so if I have my u equal to tangent x, then my du is going to equal secant squared x dx. Okay, so that would give me this as tangent x equals u. The secant squared x, well, we just talked about that. We could rewrite that as tangent squared x plus 1. So that looks like a great way to do it. Let's go ahead and rewrite. So I've got the integral of tangent to the 6th x times tangent squared x plus 1, and then times secant squared x dx. Now we can do our u substitution, and we have u equals u plus 1, u to the 6th, and u squared plus 1, and then du. So multiply that through. We have the integral of u to the 8th plus u to the 6th du, which then equals 1/9 u to the 9th plus 1/7 u to the 7th plus c. So these ones are really kind of a step back from what we have been doing. Definitely not as involved integral as section 3.1 was. Okay, go ahead and put it back in our tangent x, and we get a final answer of 1/9 tangent to the 9th x plus 1/7 tangent to the 7th x plus c, and we are done.